Okay, so now let's take a look. What did we actually code up? Well, we have only 20 points here. Let's have a bit more points and see how this works. And actually, let's make. So this is called something I often use. A naming convention in the files is that there's something comp, and then there is a corresponding file with the same name up to here, and then it's plot. With the idea that sometimes computations take a long time. I mean, they can take overnight or days sometimes, or at least even if they take like 30 minutes or 10 minutes, it's nicer to first compute and save the results, and then when you plot and modify the plot and make it as well visualized as possible, then it's nice not to have to compute all over again. So the strategy here would be the same. So let's save this by the name plot, and then we have to start actually by loading the previous results. Let's just put it here. Show the results of deco 0101 on model plot. No, comp. And here load, and then so now we have this X and convres. So let's see what happens with this. There is nothing, which is very weird. Or what is X? X is such, and let's run it again. Oh, it should be xvec, of course. Xvec should be saved. So let's run that. And now you see the warning directory already exists, but just ignore it. It doesn't matter at all. So actually here we have to take this xvec and vec. So now hopefully we see something like this, and it I think would be instructive to first of all have some control over the plot, how it looks. Let's put here even 2, and maybe it would be also nice to plot the original target f at xvec. This maybe by black line, and this one with red line, and hold on in between. Let's see. Okay, I would say we see two things. First of all, our A may be a bit too big because our function is spread out pretty much hopelessly. And on the other hand, I think our integration is not so accurate, and I think we need more points. Definitely we need more points here in the integration, and I think we could use also some more points here. Let's run it. It took a little bit more, oh, well, not too much more time. And now, so now the result looks a bit more smooth, although it seems to me that there is some weird. So I think our integration is not really doing such a great job. There's something really weird going on. Do we have... But anyway, let's make this a bit smaller. Let's divide it by 10 and let's see what happens. Let's have here some more points and maybe here also some more points and see what happens. Okay, so now we are not destroying our signal as much as before because A is smaller, so we have a more narrow point spread function. If we zoom in, it seems to be much more smooth, this one. But I think let's still have, let's take 10,000 points here, a couple of more, twice the points here, compute. Now it already took some half a second to compute. And maybe we could even thick line and thin line. So this could be 1. Let's see how this works. Okay, looking like that. And I think we could make A a little bit bigger, so to have a bit more convolution to correct for. So maybe let's try something like 0.4. Maybe this is even a bit too much. Let's try something like that. Okay, I think this could be something we can live with, especially since this large step has been quite drastically removed. So can we build it back up? And also we see here, you see this flat part here. It means that our normalization with the half disk area is correct. So thank you for that. Especially because we didn't have to integrate this stupid integral. And also here, it's kind of nice, there is something for us to correct even in the smooth part. So this could be a nice situation for us. And then we could make a function. Let's do it from here. I'll save this with a new name. So let's call this continuum model measurement. And that will be a function now. Evaluate the continuum model convolution. And I think we can steal from here these arguments. Evaluation point, real number in the interval from 0 to 1, because that's where we want to work, and returns value of convolution between PSF and target F at point X. So we have a function, we have the result, cont meas at X. Then let's check x values are in the interval. So let's put it this way: if max x is bigger than 0, or minimum of obs x, and let's also drop this as a vector. Yeah, no, not easy.
Just wanted to check, because
Yeah.
in the conf script that we did earlier,
Yes.
we save the data into .dat.
Yes.
And then we're loading it here to build the function.
Yes.
But you said that .dot file is not necessary, just students are confused when it's not there.
No, the confusing thing is to have a folder called data instead of saving the mat files into the same working folder. But I don't want them there because there may be a big number of mat files resulting all the computations. So then there will be so many files in the same working folder. So that's why I like to have a subfolder called data and save. But it should be there. Oh, you're right. I mean, this should be. Oh man, this should be there, and we should save it there. So many mistakes. So this one, we should save it there, and also the plot function. Where is it? This one. So also here. Because here in our working directory, so now the conv data is here, and I really don't want to have those there. I want to have them in the data folder. Failed to do so though, but anyway, let's correct now. So let's compute this one again. So now we should have the data here. So that was the confusing thing, to have this folder. Yeah, but now it's there, and let's just keep using it throughout the course, and let's not get confused by it. It will make things simpler because there can be dozens of mat files in this area. It's better than they are not here. That's the only thing. Maybe I'm confusing more with my explanations than actual deeds. Anyway, what are we doing? Yes, this measurement thing. So now we want to check that the x values are in the interval. So the minimum should be if max is more than 1, and or if minimum is less than 0, then of x should be in the interval 0 to 1. Like this, then load the results, and then evaluate the function using interpolation. So what happens here is that
Few things.
yes.
I think you have the or sign, only one there. This if max ups
Should be
yeah.
2.
Yeah, I mean.
Here, you think it's 2?
I don't know, but usually.
I just checked right now.
Okay, can be that. Okay.
I think one works. Yeah.
I don't know if I read the code.
Mm-hmm.
Because I think you say min obs. How can it be like under 0 if it's like abs?
Excellent. Yes. I was kind of thinking that if someone is feeding complex vectors or something, let's not care about complex things. Let's stick with the simple things. Excellent. So now maybe it's more reasonable.
There is also a right parenthesis missing in the minimum. No, there's one too much on the left side, I think.
Let's see. Oh, this is okay. This is okay. Okay,
Yeah,
I think the parentheses are right. Whew. Okay, and then we use interpolation. And interpolation works like this. We give the interp1 function, we give it a function, evaluation points and a function. So these are the points, and this function is given at those points, and then we want to know the values of the function at some other points, in this case the x, that is the argument. And then we can also choose how to do the interpolation. There are several options, for example, nearest neighbor, which gives kind of a discontinuous option. There's a linear one that uses just linearly between the known points. I think we could do spline, which gives a continuously differentiable approximation. Because theoretically we know that our function should be, I think it should be continuously differentiable, so this should be quite okay. So now I think we should be able to plot this measurement. So actually I think we can go on and make our function that finally creates our continuum model data vector. That's what we have been now aiming for. So now let's say simulate noisy data from the continuum model of convolution. So now our goal is, first of all, choose number of data points. And now remember that in this part of phase of the course we are working with measurement models with n. I mean, our m and final result f are both vectors in Rn. So that's the n we shall be using. So let's, for example, let's take 64 points to start with. That's something we can change later. And then evaluate ideal data. So m then is, what should we call this? Let's call this deco 02, and let's call this data comp. So now we are computing the data which we want to invert later. So we are simulating continuum model data. And here ideal means not noisy. So then we have our function construct data points . So now we want to construct these points, these ones here. So the xvec is, let's see what it is. It should be, at least we need 1 over n. That's the step between the points. The first one needs to be 0, 0, and then we want altogether n points, so this should be n minus 1. So I think these are our x points where we want to evaluate. And so we evaluate it here. Then let's see how this looks like. Let's see how this looks like. And actually, I want to also plot our actual measurement without sampling at those points to compare with. So let's take fine x points from 0 to 1 and with quite many points. So let's first plot fine x and then this conv meas at those points. This in black. Then hold on and then plot our what we construct right here. We have this our x vec in 64 points or in n points. Let's plot x vec and our m with black dots. Oh, cont meas, it's not conv meas, it's okay. Okay, so here we see the function of a continuum variable, our psi convolution f. That function, this function right here, is defined for every real number between 0 and 1, and we have simulated that one with quite high accuracy. And that I'm showing with this continuous curve there. Let's actually have these, where do we have these plot files here? Let's have these plot parameters, and also we need marker size. Let's see what would be good. So here, let's call this thin line. And this one with marker size. Let's take a new look. Okay, now it's a bit clearer. And now we can, of course, have more points if we want. This, of course, now depends on our measurement device, at how many points can we sample, but this is something we will take a look at when n becomes bigger in our inverse problem, with the idea that when our computational model is getting higher dimensional, everything should be becoming more accurate. As a general principle in computational mathematics and numerical analysis, we'll see a couple of strange little things happening there, I predict. And then let's evaluate noisy data. Let's again call it mn, and this is m plus noise. So noise would be, let's again have this sigma, let's point 0.1, for example, 10% noise. Noise would be sigma times rand n size m, and here this is just m plus noise, and let's plot it here in red. Okay, our data is rather noisy. Maybe we could use a little bit smaller standard deviation. Let's just put 1% noise. So you see they are a little bit randomly scattered around the point where they should be. And now actually I think we could do these two in blue, and we could also include our target F in black, let's say. So there's our original signal function we would like to recover. However, I mean, as shown here, the target F is a function of a real variable. In a computer, how can we recover it? One of the options is, similarly to what we did to the convolution function, to sample F at those very same points. So we could let me plot this at xvec, and so now I think maybe let's move back to a little bit less points so the plot is not so busy. Maybe we can see better what's going on. So now there's a lot of information in this graph. Let's see what's going on. So the black function is our target that has jumps and all that. The black dots are the values of our target function at the grid points. Those are the ones we want to know. That's our goal in the inverse problem, to know the location of those black points. That's the goal. However, what we are given is the red points. So there are a couple of processes going on in the construction of the red points. There is the continuum convolution between the point spread function and the target F function. That's the blue line. Then the blue line has been sampled at the grid points. Those are the blue dots. And then on top of that, there is some random noise in our measurement device, so we get the red dots. And now the thing is, from the red dots, we should get to the black dots with some computational method. That's the topic of the course. And now, for that, we need to build yet another model, a computational model. I'll stop this video now here and